Welcome to Meteorology Matters. What if we told you that humanity's really profound influence on Earth's climate, the very air around us might have been detectable much, much earlier than we previously imagined?
Yeah, we're talking about a time when, horse-drawn carriages were still the main way to get around.
Exactly. Long before gas-powered cars were even a common sight. It's a revelation that genuinely shifts our understanding of climate history and, well, our long-term impact.
hmm
Today, we're embarking on a truly captivating journey, sort of a scientific thought experiment, really, to explore precisely when the human impact on our atmosphere became, undeniably discernible.
It really challenges so many assumptions about the timeline, doesn't it?
It does, pushing that moment of clear detection back over a century.
That's right. Our mission in this Meteorology Matters exploration is to unravel how scientists, kind of peering back through time but using today's advanced tools and sophisticated climate models,
Yeah.
have pinpointed a precise moment.
A moment when a human fingerprint would have emerged. Yeah.
Exactly. In the atmospheric temperature record. And this isn't just, a historical curiosity for scientists. It fundamentally reshapes our understanding of humanity's long-standing and often overlooked connection to global atmospheric changes.
It really makes you consider just how long we've truly been altering our planet on a planetary scale.
It really does.
So, if we're tracing this impact, where do we even begin? Where do we see the earliest scientific glimmers of understanding how our atmosphere actually
Yeah,
works?
what was the foundation?
Right.
Uh,
What set all this in motion long before anyone even thought of a carbon footprint?
that's a great place to start because the groundwork was laid surprisingly early. Picture the mid-19th century,
Okay.
a time of incredible scientific curiosity discovery.
Hmm.
Even while the Industrial Revolution was, rapidly expanding,
Right.
a handful of visionary scientists were quietly unraveling the fundamental physics of Earth's atmosphere.
And who were these pioneers? What did they actually uncover?
Well, the absolute foundation of our understanding of the greenhouse effect comes from the late 1850s, early 1860s.
Okay.
This is when two really brilliant individuals, Eunice Foote and John Tyndall, working independently, mind you, conducted these pivotal experimental discoveries.
Ah, Foot and Tyndall.
Yes, they were the first to really demonstrate the heat-trapping properties of carbon dioxide
Huh.
and other greenhouse gases, too.
How did they even do that back then?
Well, you can imagine their labs. They'd fill these glass tubes with different gases, right? Then expose them to sunlight, measuring how much heat each gas absorbed.
Simple but clever.
Very. And Foote, who's actually a self-taught scientist and a women's rights advocate, she even hypothesized that an increase in atmospheric CO2 would lead to a warmer planet.
Wow, back then.
Absolutely, predicting something remarkable for her time. Tyndall later confirmed and expanded on her work, adding critical detail about the specific wavelengths of heat that CO2 absorbed.
So these are like the seminal moments.
Definitely. Essentially identifying the very mechanism that allows our planet to stay warm enough for life, but also, critically, how it could be altered.
So they showed certain gases act like a blanket, trapping heat. But did anyone before them have inklings of this? Was the idea totally new?
Good question. No, not entirely new, but the experimental proof was. Earlier thinkers like the French mathematician Jean-Baptiste Fourier back in the 1820s had already proposed that the Earth's atmosphere played a crucial role in keeping it warm.
He compared it to a greenhouse, right? Or a hot box.
Exactly. Then Claude Pouillet in the 1830s refined these ideas, and even earlier, the Swiss naturalist Horace Benedict de Saussure, late 1700s, he did experiments with something called a heliothermometer.
The one now?
Heliothermometer, basically an insulated black box designed to trap solar radiation. So it hinted at how the atmosphere might work.
Okay, so the theory was kind of brewing.
The theoretical stage was set, yeah. But it was the meticulous experimental work of Foote and Tyndall that really solidified the understanding of specific gases as the heat trappers.
Got it. And this brings us to a name many might recognize. Svante Arrhenius.
Ah, yes, Arrhenius.
What was his big contribution to this?
Arrhenius, a brilliant Swedish chemist, came along in the late 1800s, building directly on Foote and Tyndall's work. And he made what was, for its time, just an utterly astounding and prescient prediction.
Okay.
He was one of the first to really recognize that the burning of fossil fuels, mostly coal, back then during that big industrial push, was increasing the amount of carbon dioxide in the atmosphere.
Right, that makes sense.
But he didn't stop there. He went a remarkable step further. He actually estimated, that a doubling of atmospheric carbon dioxide could lead to a surface temperature increase of around 4 degrees Celsius.
Wait, hold on. 4 degrees Celsius, it sounds uncannily familiar. Isn't that close to modern estimates for climate sensitivity?
Bingo.
He figured that out over a century ago.
Precisely. It was a profoundly insightful calculation based on the best available physics and observations of his time,
Yeah.
made more than a century ago. He wasn't just guessing. He was using scientific principles to anticipate a key aspect of climate change with incredible foresight. He understood the mechanism and even estimated its magnitude long before anyone could have imagined the scale of fossil fuel use we see today.
That's incredible. So the theory was there, the understanding of how CO2 warms the planet was emerging, but to actually detect a human influence, you need data, right? Observations. What was happening on that front?
You're right. Theory needs proof, needs observation.
Blue.
And in parallel with this developing theoretical understanding, the practical data needed to identify these human fingerprints was kind of slowly but surely accumulating.
Okay.
By the 1860s, systematic daily measurements of surface temperature had begun, mostly in urban areas across Europe and North America.
So like weather station data.
Pretty much. This
Mhm.
provided a foundational record of localized temperature changes, establishing a baseline of sorts.
But surface measurements alone, that wouldn't give you the full atmospheric picture, would it? You need to go higher up.
Exactly. To truly understand global climate and the vertical structure of temperature, scientists needed to look beyond the surface. They needed to venture into what they called the free atmosphere.
The air mass is above the ground.
Right. And that was a significant challenge for the technology of the time. However, pioneering efforts started in 1892. A French physicist, Gustave Hermite, and a journalist, Georges Besançon, launched some of the first unpiloted weather balloons.
Unpiloted balloons in 1892.
Yep. And they weren't just balloons. They carried these compact devices designed to measure temperature and pressure high above the ground.
That's amazing. Just sending stuff up and hoping for the best.
Kind of. It's
Wow.
incredible to think of them just sending up balloons, completely unaware they were laying the groundwork for discovering an entirely new atmospheric layer. What a leap of faith and ingenuity.
So they were essentially sending up little weather stations on a string almost.
Precisely. And their work paved the way for more systematic, balloon-based measurements toward the end of the 1800s, notably by Léon Tesserent de Bort in France and Richard Assmann in Germany.
Okay, more systematic efforts.
Yeah, they used balloons made of paper, silk, rubber, constantly refining their techniques. And what they discovered was truly groundbreaking.
What was it?
They found that temperature didn't just keep dropping the higher you went, which was the common belief.
Right, colder, higher up.
Instead, they observed a distinct layer above roughly 11 to 14 kilometers, where the temperature either stabilized or even increased with height.
Increased. That's counterintuitive.
Totally unexpected. And that finding marked nothing less than the discovery of the stratosphere, a whole new layer of our atmosphere.
Wow. The stratosphere, that's a huge discovery. How did that early balloon tech evolve into, what we use today?
Well, these early experiments, where they often had to recover the instruments manually,
Right, finding the balloon.
yeah, they rapidly led to the development of what we now call radiosondes. That was a massive technological leap.
Radiosondes. Okay.
Imagine a small weather balloon carrying a compact instrument package, maybe the size of a shoebox, measuring temperature, pressure, humidity. But crucially, unlike the earlier ones, radiosondes could transmit these measurements directly down to ground stations via radio.
Ah, real-time data.
Exactly, real-time data from much higher altitudes as they went up.
Yeah.
It revolutionized atmospheric observation. Now, truly global records of free atmosphere temperature didn't really kick in until around 1946, or maybe more broadly with the International Geophysical Year in 1958.
IGY 58, right.
But statistical reconstructions using historical upper air and surface data can even extend back as early as 1918, so the observational network was definitely growing.
Okay, so we're getting temperature data from higher up. What about the historical chemical record? How did they know what CO2 levels were actually like way back then before Arrhenius?
That's where Earth itself acts as a kind of historical archive.
Oh, so.
In the vast ice sheets of Antarctica and Greenland, these ice cores act like frozen time capsules.
Right, the ice cores.
As snow falls and compacts over millennia, it traps tiny bubbles of ancient air. Scientists can drill down, extract these cores, sometimes hundreds or thousands of meters deep, and analyze the air trapped in those bubbles.
A direct sample of past air.
A direct sample of Earth's past atmosphere. They've revealed precise historical signals of carbon dioxide, methane, other greenhouse gases, going back hundreds of thousands of years, way before the Industrial Revolution.
So what did they show for the period we're talking about, the late 1800s?
From those cores, we know that between 1860 and 1899, atmospheric carbon dioxide was growing at a rate of approximately 2.5 parts per million by volume per decade.
Okay, so a measurable increase even then.
A measurable increase.
Yeah.
So you had the theoretical understanding from Arrhenius, the developing observational methods for the atmosphere, and now, thanks to ice cores, a detailed historical chemical record. The pieces were starting to come together.
So by the late 1800s, early 1900s, the picture was emerging. Burning fossil fuels released CO2. CO2 enhanced the greenhouse effect that would warm the surface. And the ability to measure atmospheric temperatures was advancing fast. But, and this seems like a big but, there was still a crucial missing piece, wasn't there? Something preventing them from getting the full picture.
You've hit on the critical point.
Yes.
They knew broadly that CO2 would warm the surface, but they didn't yet have a clear understanding of exactly how these elevated CO2 levels would specifically change the vertical structure of atmospheric temperature.
Meaning?
Meaning they didn't fully grasp the distinct and different effects on the stratosphere versus the troposphere, that lowest layer where we live, where weather happens.
The cooling versus warming pattern.
Precisely. That critical understanding, the detailed modeling works that could show those precise vertical changes, wouldn't become available until much, much later, specifically with groundbreaking modeling work published in the 1960s.
Wow, the 1960s, that's a significant gap.
A huge gap between the initial theory and the ability to detect the specific pattern, the unique fingerprint of human influence.
And that missing piece, that later development of sophisticated climate models, brings us right to the core of this fascinating research we're discussing. The central question the scientists posed was, well, it was truly audacious, wasn't it?
It really was.
When could scientists first have definitively known that fossil fuel burning was significantly altering the global climate if they had access to today's advanced tools and models?
Yeah, the big what if.
And this contrasts sharply with a lot of previous studies, right? Which mostly looked at surface temperature changes or maybe paleoclimate reconstructions.
Exactly. Those often suggested a later detection time for human influence, sometimes well into the 20th century.
But this study took a different angle.
What's unique about this particular research, and why it's so compelling, is its deliberate focus on the stratosphere.
Why the stratosphere?
Because that upper layer of the atmosphere is expected to show a remarkably large human-caused signal with very distinct patterns of change. Think of it this way. The stratosphere is like a quiet room. A small sound in a quiet room would be much easier to hear than in a noisy concert hall, right?
Right. The concert hall being the troposphere.
Pretty much. The troposphere has much more natural variability, more noise. So the stratosphere makes the signal potentially much clearer, easier to detect, especially early on. It's a strategic move to find the earliest possible evidence of our impact.
So if we're going back in time, hypothetically, with today's tech, how did they actually construct this scenario? It sounds like something out of science fiction, this Gedanken world.
It's an ingenious approach, this Gedanken world, a thought experiment world.
Yeah.
To answer the big question, the researchers constructed this simulated scenario with some key assumptions.
Okay, what were they?
First, they assumed that global monitoring of atmospheric temperature, with the kind of accuracy we achieve today, could have existed as early as 1860.
Wow. So imagine super accurate sensors everywhere back in 1860.
Exactly. A network of highly advanced radiosondes, or even early satellite-like instruments, beaming back perfectly accurate data from every corner of the globe, right from 1860.
That's a huge what if. What else do they assume about these futuristic historical instruments?
They went further. Second, they assumed that any instruments available back then, in this hypothetical world, would have had the same incredible accuracy as today's satellite-borne microwave radiometers.
Okay, the really precise ones we use now.
Yeah, these sensors measure microwave radiation emitted by oxygen molecules, allowing for very accurate temperature profiling. So this assumption just eliminates any technological limitations of the past. It lets them isolate just the climate signal itself.
And they input data for their models, the CO2 levels and stuff.
Third, they ensured that the climate model simulations they used for this historical analysis had access to completely reliable estimates of carbon dioxide changes.
Using the ice core data and direct measurements we talked about.
Exactly. Drawn from those ice core records, and later direct air measurements, providing the models with a perfectly accurate historical precedent, forcing the driver of the change.
So, armed with this idealized historical data and today's super accurate tools, What were they actually hoping to achieve with this thought experiment? What were the goals?
This experiment had dual ambitious goals. Primarily, it aimed to estimate the detection times of human-caused temperature fingerprints across different atmospheric layers, stratosphere, troposphere, and across various geographical regions.
Okay, so when and where could it have been detected?
Right. But it also aimed to understand how those detection times would vary based on different choices of the assumed start date for this hypothetical monitoring.
So starting in 1860 versus, say, 1900.
Exactly. They explored a wide range of start dates, from that initial point in 1860 all the way up to 1986.
Why 1986?
That's when truly global satellite records of atmospheric temperature change actually began in the real world. So this allowed them to see not just when a signal could be detected, but how that detection time itself shifts depending on when you start observing.
Fascinating. And central to this whole thing, you mentioned a technique called fingerprinting. Can you explain that a bit more? How do you fingerprint a human climate signal?
Yeah, the fingerprinting method is really the cornerstone here. It's a powerful statistical technique used in climate science. Its job is to distinguish human-caused climate effects from natural variations.
Like picking out one voice in a noisy crowd?
That's a great analogy. Fingerprinting looks for unique patterns, like the distinctive sound of a human-caused climate signal amidst the background noise of natural climate variability.
And the climate system has a lot of natural noise, right? El Nino, volcanoes?
Exactly. El Nino, volcanic eruptions, solar cycles. The system is inherently noisy. So you need a robust way to confidently say, okay, this pattern we're seeing isn't just natural noise, this is us.
So they're looking for a specific signature, a specific pattern.
Precisely. Specifically, this method searches for particular model-predicted patterns of atmospheric temperature change that are characteristic of combined human and natural influences.
And for the human fingerprint, that pattern is?
It's very distinct, characterized by stratospheric cooling and simultaneously tropospheric warming.
That vertical structure again.
Exactly. It's not just a uniform change across the whole atmosphere.
Yeah.
It's a specific, vertically differentiated structure of warming and cooling that models predict our emissions would cause. It's like a unique barcode for human influence.
And how do they know when that signal, that barcode, is strong enough to be considered a definitive detection, not just a random blip?
Good question. The confidence in detection relied heavily on what scientists call signal-to-noise ratios.
Okay.
Think of our crowded room analogy again. If the specific voice you're listening for is barely audible, the signal-to-noise ratio is low. If the voice gets much louder or the background chatter quiets down, the ratio improves.
Makes sense.
For detection to be considered robust in this research, the human-caused signal had to be significantly larger than the natural background variability. Specifically, the signal-to-noise ratio had to remain above a 1% significance level for a sustained period.
1% significance, that sounds pretty strict.
It is. It means there's less than a 1% chance that the observed pattern is just due to random chance or natural fluctuation. It's a very high bar for certainty.
Okay, here's where it gets truly fascinating. The results of this hypothetical experiment, they were absolutely startling, weren't they? Especially for the stratosphere. So what did this thought experiment, this Gedanken world, reveal first?
Well, the headline finding, the one that really makes you pause,
Yeah.
was that a human-caused stratospheric cooling signal could have been confidently identified by approximately 1885.
1885. Let that sink in. That's a century before many people even started talking about climate change seriously. Before cars were common, before widespread electricity. How is that even possible?
It's astonishing, isn't it? That's just 25 years after the hypothetical 1860 monitoring start date.
Just 25 years.
And what's more, even if this hypothetical monitoring in 1860 hadn't been global, say we only had high-quality stratospheric temperature measurements in a limited region like Northern Hemisphere mid-latitudes,
Yeah.
detection was still feasible by 1894, nearly 34 years after the assumed start.
Why that region specifically?
That region, the Northern Hemisphere mid-latitudes, actually aided early detection because it generally exhibits lower natural temperature variability in the stratosphere compared to, say, the more dynamic polar regions.
So it was a quieter place to listen for the signal.
Exactly. Made it easier to spot the emerging human signal.
And the scale of the emissions back then, compared to now, it must have been minuscule.
Precisely. What makes this even more profound is the scale of the change at this early stage. The decadal increase in atmospheric CO2 between 1860 and 1899 was roughly 10 parts per million total.
Okay, 10 ppm over about 40 years.
Right. Compare that to the first 25 years of the 21st century, 2000 to 2025, where CO2 levels shot up by about 50 parts per million.
Wow.
So the increase in the late 1800s was a factor of 9 smaller than what we've seen recently. Yet, the signal was apparently clear enough to be detected in the stratosphere, hypothetically.
So why the stratosphere first? What makes that specific layer so sensitive to our emissions, and why does it show this cooling signature? It seems backward.
Yeah, it seems counterintuitive, but there are compelling physical reasons. First, as we touched on, anthropogenic increases in CO2 lead to a very pronounced cooling of the mid to upper stratosphere.
Right, unlike the troposphere, which warms.
Exactly. Think of it this way. CO2 in the troposphere acts like a blanket, trapping outgoing heat from the Earth's surface. But in the stratosphere, the increasing CO2 means more heat is radiated away from the stratosphere directly out into space.
So it becomes a better radiator at that altitude.
Precisely. It becomes a more efficient radiator of energy from that altitude.
Okay, so it's like the CO2 is acting as a window for heat to escape from that specific layer.
That's a good way to put it. Second, the pattern of this human-caused cooling is remarkably distinct. It differs markedly from the patterns of natural variability, making it easier to pick out.
The unique barcode.
Right. Third, this CO2-induced stratospheric cooling actually amplifies with increasing height. It gets even stronger the higher you go into the stratosphere.
How much cooling are we talking about?
Over the entire simulated period, from 1860 to 2024, the multi-model average global mean stratospheric cooling ranged from about 1.1 degrees Celsius in the lower stratosphere to a significant 6.0 degrees Celsius in the upper stratosphere.
6 degrees, that's a huge temperature shift over time.
It is. And the primary mechanisms for this cooling involve that increased long-wave emissivity from CO2 radiating more heat away, and also ozone losses, particularly later in the 20th century. Ozone absorbs solar radiation, so less ozone means less absorption, leading to further cooling.
So multiple factors reinforcing that cooling signal.
Yes. It's a very clear, strong signature that doesn't get easily drowned out by natural noise, especially compared to the troposphere.
Okay, so while the stratosphere provided this early, striking signal, the troposphere, the layer closer to home where weather happens, told a different story. What did the models reveal about temperature trends down there?
Right down below, it's different. Unlike the stratosphere, the two tropospheric layers looked at the lower and the total troposphere have consistently warmed in both the satellite data we have and in the climate models.
Which is what we generally associate with global warming.
Exactly. That's the warming we feel on the surface, the warming that impacts our daily lives. The multi-model average warming simulated from 1860 to 2024 for these layers was about 1.2 to 1.3 degrees Celsius.
Okay, so it was warming down there too. But why wasn't the human signal detectable as early as in the stratosphere? If it was warming, shouldn't that be obvious?
Ah, that's the crucial distinction. Despite this warming, robust, anthropogenic fingerprint identification in the troposphere was not feasible with an 1860 monitoring start date and only 40 years of hypothetical data.
Not feasible. Why not?
The human signal simply wasn't strong enough yet to clearly stand out from the natural background variability in that layer. The noise was too high relative to the signal.
So when did it become clear in the troposphere, according to the models?
Consistent detection of human fingerprints in tropospheric temperature only occurred for assumed monitoring start dates on or after 1960.
1960, that's a significant delay compared to the 1885 potential in the
A
stratosphere.
very significant delay.
So the noisy concert hall analogy really holds true here then. The human signal, the warming was there, but it was just harder to pick out from all the other sounds.
Exactly. And the reason for this delay is multifaceted. Firstly, as we said, the global mean anthropogenic signals are generally smaller in magnitude in the troposphere compared to the dramatic cooling in the stratosphere.
Okay, smaller signal.
Secondly, and this is critical for the fingerprinting method, the signal patterns from human influence and the noise patterns from natural variability are more similar in the troposphere.
Ah, so they look more alike.
Yes, they tend to blend more, making it inherently harder to distinguish the human influence from natural ups and downs early on.
Okay. Any other factors?
Furthermore, the rate of warming in the troposphere only saw a really significant increase after approximately 1980.
Why after 1980?
This acceleration was partly due to controls introduced on anthropogenic sulfur emissions, mainly in the late 1970s and early 80s. Think acid rain regulations.
Right, sulfur pollution.
Prior to those controls, sulfate aerosols from human industrial activity actually had a damping cooling effect on the troposphere. They reflected sunlight.
So they were masking some of the greenhouse warming.
Effectively, yes. They were masking some of the underlying warming trend from greenhouse gases. Once those aerosols were reduced, the greenhouse gas warming signal became much more apparent and accelerated.
So, natural forces and even other human pollutants can act as a kind of cloak, temporarily obscuring the main CO2 signal. Let's talk more about that natural variability. It's not just CO2 driving things. How does something like a massive volcanic eruption impact this detection process?
Volcanoes are indeed powerful short-term disruptors. Large explosive eruptions, think Krakatoa in 1883, Pinatubo in 1991.
Agum, El Chichon.
Right. Those inject vast amounts of sulfur dioxide high into the stratosphere. This SO2 converts into tiny sulfate aerosols that reflect sunlight.
Okay, and these cause temperature changes.
Oh, yes. Very distinct short-term signals.
How do they affect the stratosphere specifically? We know CO2 cools it.
Right. Volcanoes do the opposite, temporarily.
Hmm.
In the stratosphere, especially the lower stratosphere where most of the volcanic aerosol hangs out, these eruptions cause a temporary warming signal.
Warming. Why warming there?
The aerosols absorb some radiation at that altitude.
Hmm.
This warming typically lasts 1 to 3 years. So it's the exact converse of the long-term cooling signal from CO2.
Right. So a volcano could temporarily cancel out or mask the human cooling signal there.
Exactly. It can temporarily counteract the human fingerprint in the stratosphere, making it harder to spot, like someone briefly turning up background noise.
And what about down in the troposphere? We usually hear volcanoes cause cooling.
Correct. Down in the troposphere, these same eruptions cause short-term cooling signals. This generally lasts a bit longer, maybe 3 to 5 years.
Because the aerosols block sunlight from reaching the surface.
Precisely. So what this means for our detection timeline is that volcanic activity can temporarily cause the human signal, either stratospheric cooling or tropospheric warming, to dip below the detection threshold.
Briefly delaying recognition.
Yes. For instance, the study notes that the massive Krakatoa eruption caused a noticeable dip in the signal-to-noise ratios around 1883-1885, momentarily obscuring the human fingerprint just as it was trying to emerge in that hypothetical 1885 detection scenario.
Interesting. And the tropospheric cooling lasts longer.
Tends to, yes. Volcanic temperature signals generally persist longer in the troposphere than the stratosphere, largely due to the huge thermal inertia of the ocean.
Ah, the ocean takes longer to cool down and then warm back up.
Exactly. It holds onto that volcanic chill for longer.
Okay, so volcanoes are big, short shocks. What other natural forces create this noise or maybe ripples in the signal? I'm thinking about the sun itself. Does solar activity play a role?
Excellent point.
Yeah.
Yes, beyond volcanoes, solar variability also plays an important role, primarily through its roughly 11-year cycle.
The sunspot cycle.
Right. The total solar irradiance, or TSI, the total amount of solar energy Earth receives fluctuates slightly on this rhythm. It varies by a small percentage.
And that affects temperature.
It does. This fluctuation causes coherent stratospheric warming during periods of high TSI, when the sun is more active, and corresponding cooling during periods of low TSI.
Okay, so the sun's activity can either help or hinder us in spotting the human CO2 signal in the stratosphere.
Precisely. This natural solar forcing can either reinforce the human-caused CO2 cooling, if the sun is in a cooling phase, or partially offset it, if the sun is in a warming phase.
Making the human signal easier or harder to detect.
Exactly. It influences the strength and clarity of the human signal, especially for those early monitoring start dates when the anthropogenic signal was relatively smaller. It's like another instrument in our orchestra, either playing in harmony or slightly out of tune with our target CO2 sound.
And it's not just the regular 11-year cycle itself, is it? There are longer-term variations.
That's right. It's not just the cycle. Longer-term, lower-frequency changes in the amplitude of this 11-year solar cycle can also cause what the researchers call ripples in the human signal strength and the detection times.
Ripples, meaning?
Meaning the time required for detection doesn't always just get shorter and shorter as you start monitoring later. Sometimes, because of these solar variations, it might take slightly longer to reach detection for a later start date compared to an earlier one.
Can you give an example?
Sure. The study found that for a hypothetical 1920 start date, it actually took a bit longer to detect the signal compared to a 1900 start date.
Right.
Part of the reason was that the period following 1920 sampled larger amplitude solar cycles, meaning more pronounced solar warming periods that counteracted the CO2 cooling.
Oh.
Another ripple occurred for analysis periods ending near a solar maximum in the late 1930s. This caused the signal-to-noise ratios to temporarily dip below that significance threshold, thereby delaying fingerprint detection for start dates around that time.
So it illustrates how these natural solar forces, even though they're smaller in magnitude over the long haul compared to greenhouse gases, can still influence the precise timing of when a human signal becomes statistically undeniable.
Exactly. They add complexity to the detection timeline.
Okay, so given the hypothetical nature of this Gedanken world and all these complexities with natural variability, how much confidence can we really place in these findings, especially those really early detection times like 1885? The reliability seems to hinge on how accurately the climate models estimate that natural internal variability, the noise.
It's absolutely right.
If the models underestimate the noise, wouldn't that make the signal look clearer earlier than it really would have been? How do we know the models are getting the noise right?
That's a critical question for any modeling study like this.
Uh-huh.
You have to validate the model's background variability.
So how did they check?
Well, for tropospheric temperature, there have been quite a few studies using multiple climate models, and they generally suggest that systematic underestimates of decadal internal variability are not a major concern.
Okay.
When we compare observed variability in the troposphere using our satellite data, it generally aligns quite well within the range of variability the models produce in their control runs.
Control runs being simulations without human influence.
Exactly. They just run the model with natural factors to see its inherent variability. The fact that the model's natural variability matches what we actually observe in the troposphere gives us pretty good confidence in the tropospheric findings and detection times.
Okay, confidence is good for the troposphere. What about the stratosphere, though? That's where the really early detection happened. Is the confidence as high there?
The stratosphere, however, presents a bit more nuance. There are simply fewer direct, long-term comparisons available for stratospheric temperature variability between models and observations.
Less data to compare against.
Essentially, yes. We just haven't been observing the stratosphere globally for as long or as comprehensively. Now, while some studies show models sometimes have smaller variability in their control runs compared to observations.
Which would support the idea of maybe detecting too early.
Right. But it's also true that the observed variability, the real-world noise, can sometimes be inflated by factors that aren't fully included in the standard historical simulations used for fingerprinting.
Like what?
For instance, specific unusual volcanic eruptions, like the huge Hunga Tonga event in January 2022. That injected massive amounts of water vapor into the stratosphere, causing unusual temperature effects not typically simulated.
Ah, okay.
Or there might be small mismatches in the assumed solar forcing used in the models versus what actually happened, especially in recent years after 2014. These things can make the real world appear noisier than the models might otherwise predict based only on CO2, standard volcanoes, and solar cycles.
So it's complex. There might be slight underestimates of model noise, but also factors making the real world seem noisier than the model baseline.
Exactly. It's a nuanced picture.
So despite these nuances, how robust is the conclusion that a human fingerprint could have been detected so early, back in 1885 in the stratosphere? Does the uncertainty undermine that finding?
That's the key question. And the answer, based on this research, is that the conclusion remains incredibly robust.
How so?
Even if there were some degree of underestimate of stratospheric variability in the models, the observed and modeled stratospheric cooling trends are just so substantial, so large.
The signal is huge.
The signal is huge. Model variability would need to be biased low by an order of magnitude, a factor of 10, to fully explain away those cooling trends as just natural variability.
A factor of 10 error? That seems unlikely.
Highly unlikely, based on everything we know about atmospheric physics and model performance. In fact, if you recalculate the signal-to-noise ratios using the observed variability instead of the model's internal variability, the ratios remain incredibly strong.
How strong?
They reach levels of certainty comparable to what scientists call 5 sigma in physics. That's the level often used to confirm the discovery of a new particle, like the Higgs boson.
Wow. So virtually impossible for it to be just random chance.
Essentially, yes.
Yeah.
The signal is that clear in the stratosphere.
Okay. And what about when global satellite records actually began in the real world around 1986? Did the signal become even clearer then across the board?
Absolutely. That's another striking result. For monitoring, starting in 1986, when we actually got comprehensive global satellite data, the human fingerprint was detectable with high confidence across all atmospheric layers, stratosphere and troposphere, and across all geographical regions.
Everywhere.
In every single one of the 32 different climate model simulations used in the study.
Every single model run showed it.
Every single one. And this is true despite the significant counteracting effects of the 1991 Mount Pinatubo eruption, which, as we discussed, initially warmed the stratosphere and cooled the troposphere.
So even with that huge volcanic disruption.
Even with Pinatubo's disruption, the underlying anthropogenic signal was simply strong enough to emerge clearly through that substantial natural noise by that point. It provides overwhelming confidence in the detection methods and the strength of the human signal, especially from the 1980s onwards.
The message seems clear then. The human signal, particularly in the stratosphere, is powerful, it's distinct, and it has been for a very long time.
That sums it up well.
This entire thought experiment provides truly compelling evidence. It suggests that with suitable, high-quality temperature measurements, the kind we hypothetically gave the past a discernible human influence on global climate, could have been detected way back, maybe by the end of the 19th century.
Yeah.
And this isn't just a hypothetical could have been, is it? It underscores a profound reality. Significant human interference with Earth's climate is not some new phenomenon of the late 20th or 21st century.
Not at all.
It has been present and leaving its mark for over 130 years.
It's a critical reframing of the timeline, isn't it? And consider the stark contrast.
Mm-hmm.
Those relatively small CO2 increases in the late 1800s were apparently enough to leave a clear, identifiable mark on the stratosphere.
Right.
Whereas today, our increases are far more rapid, far more extensive, and far more impactful across the entire climate system. This historical perspective really gives us pause.
It forces us to recognize the long-term cumulative consequences of our industrial advancements and just how far back our planetary influence truly extends. And this leads us directly to the critical need for continued observation, especially of these upper atmospheric layers that gave the earliest signals. Why is it so crucial to keep monitoring, given this long history?
Well, the findings powerfully emphasize the indispensable importance of continuous high-quality monitoring of the upper atmosphere. These atmospheric temperature changes, particularly the stratospheric cooling and tropospheric warming patterns,
Yeah.
they aren't just indicators of our current climate state. They also serve as early, sensitive signals of the success or, unfortunately, the failure of our climate mitigation efforts.
Like a real-time report card.
Exactly.
Yeah.
A real-time report card on how our actions are impacting the planet's energy balance.
Yeah.
It allows us to see if policy changes, technological advancements, emission reductions, are they truly making a difference in the atmosphere?
And are there concerns that this vital monitoring capability might be at risk?
Unfortunately, yes. There are always concerns when budget discussions happen around crucial climate satellites and vital research programs. We've seen discussions around proposals affecting major scientific agencies like the National Oceanic and Atmospheric Administration, or NOAA.
Right. NOAA and NASA.
And the National Aeronautics and Space Administration, yes, and even the Department of Energy. Proposals that, if enacted, could potentially impact this long-term monitoring capability.
In what way?
For instance, we've heard about potential proposals that could, say, eliminate parts of the National Oceanic and Atmospheric Administration's Research Division, which handles critical CO2 monitoring. Or discussions about maybe cutting some climate-relevant satellite missions, or even stripping future National Oceanic and Atmospheric Administration satellites of specific climate science sensors.
So essentially, we're talking about potentially flying blind to some extent, reducing our ability to see these changes.
That's the worry. When we lose the capability to measure and monitor how our world is changing, particularly these sensitive atmospheric indicators, it undeniably makes us all less safe.
How so?
It hinders our fundamental understanding of what's happening, it weakens our predictive abilities for the planet's future, and it leaves us more vulnerable to changes we can't fully anticipate or prepare for. It's like dimming the lights in a rapidly changing room. We just lose our ability to navigate effectively.
And looking ahead, the projections for future changes in atmospheric temperature, say over the next 26 years to 2050, they're even larger than the changes simulated for the period from 1986 to 2024 that we just discussed.
That's right. The rate of change is projected to continue or even accelerate under many scenarios.
So this research, showing detection was possible over a century ago, serves as a really stark reminder that humanity is now, more than ever, right at the threshold of what the UN Framework Convention on Climate Change calls dangerous anthropogenic interference with the climate system.
Indeed. We are right there. The choices we make, collectively and individually in the very near future, like this decade, will likely determine whether or not we cross that critical threshold into truly dangerous and potentially irreversible territory.
It's not a problem for the distant future anymore.
Not at all. It's a challenge unfolding in real time, requiring immediate attention and informed decision-making based on the best possible science and observations.
We've walked through a truly captivating scientific thought experiment today on Meteorology Matters, revealing that humanity's impact on atmospheric temperature might have been detectable over 130 years ago.
Okay.
It's just a powerful reminder of how long our actions have been shaping the very air around us.
A long shadow.
It really raises a profound question, doesn't it? If scientists back in 1885 had truly understood the full implications of what that stratospheric cooling signal meant, if they'd had today's clarity, would it have prompted human societies to follow a different path, a more sustainable one?
It's impossible to know, but it's a sobering thought.
And what does that tell us about our responsibility to act on the knowledge, the much clearer knowledge that we possess today? It's something to think about.
Yep.
Now, if you're curious to learn more about the complexities of our atmosphere, the forces shaping our planet's weather, and want to keep up with current meteorology, you'll definitely want to follow our very own meteorologist, Rob Jones.
He does great work.
He does. You can find Rob on Instagram. Just search for meteorologist. Pretty easy to remember.
Yeah.
On TikTok, he's TV meteorologist. And over on YouTube, follow his channel, Rob Jones Hurricane. And you can also find the Meteorology Matters podcast playlist there for more episodes like this one.
Great resources to stay informed.
Definitely.
Well, thank you for joining us on this exploration today. We really hope this Meteorology Matters deep dive into the historical detection of human climate influence sparks further curiosity and critical thinking for you. Until next time, keep looking up.